All right, so we're going to finish up the bonding units with the nomenclature of organic compounds. Now, we're not going to dive into like actual organic chemistry, but it is important to know how some organic compounds are named because some of them you're actually going to deal with within the lab. So, organic chemistry in itself, it's the study of carbon-based compounds. Okay, so carbon compounds are primarily made up of nonmetals such as carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur. Other elements can be present within carbon compounds, which gives them special properties and abilities. But if you want to study that further, when you go into college, you want to take organic chemistry, and you'll learn all about that, trust me. Carbon has the ability to form long polymers or chains and rings of various sizes. So organic chemistry utilizes three particular formulas to identify these carbon compounds. A couple we've already talked about, like empirical formulas, which are the smallest whole number ratio formulas. And again, they're used to identify a very single basic unit of something much larger. So if I have a long polymer of carbon compounds and I really just want to identify one part of it and then say how many chains of those there are, I can do that. Molecular formulas like glucose, sugar, and stuff like that, those are carbon-based compounds. So we can just use a molecular formula to identify those. And the next one we haven't talked about is called structural formulas. Okay, this identifies and shows the structure of how these compounds look like under a microscope, at least in 2D space. So structural formulas are the graphical representation of a molecular structure of carbon compounds that shows the number of atoms present and how they are bonded to each other, single, double, triple, whatever. So for example, this is what a structural formula would look like. Isomers, okay, are compounds with the same molecular formula, but they have a different structural formula. So the same number of atoms within it, but they're bonded in a different way. So this will be an isomer of that previous one. So if I look at the number, I say, okay, I have 1, 2, 3, 4 carbons, 1, 2, 3, 4 carbons. And then I have 3, 5, 7, 10 hydrogens. Then I have 3, 6, 9, 10 hydrogens. So same exact composition of elements, but they're just bonded in a particular different way. And this difference in bonding allows them to react in different ways. Again, something further into organic chemistry, but just be aware that isomers do exist. So isomers have the prefix of iso in front of the chemical name. So if you see isopentane, it means it's the isomer of pentane, which means it has the exact same number of elements, it's just bonded in a different way. Hydrocarbons sounds exactly what it is. It's the simplest type of organic compounds that contain only hydrogen and carbon. Okay, hydrocarbons can be broken into three primary groups: alkanes, alkenes, and alkynes. They all three sound very different, or very similar, excuse me, but they're all very different. So it's very important to know exactly what you're talking about, because if you're talking about alkanes, it's a completely different subsect of organic compounds compared to like alkynes. So hydrocarbons are a byproduct of decomposition of animals and plants over millions of years. So fossil fuels, stuff like that, natural gas, petroleum. So you know these emissions here are made from the burning of hydrocarbons. So you know they break down to the simplest. Well, during the decomposition of bodies, they break down to the simplest form of hydrocarbons, and then that's when they become saturated, and we can use them as fuel and oil and so on and so forth. So first of all, we're going to talk about alkanes. They're carbon atoms that are bonded together by single covalent bonds. So they're hydrocarbons that have carbon atoms bonded by single covalent bonds. Okay? They can't become saturated, which means that they can conglomerate pretty easily. The generic chemical formula, this is kind of a shortcut in how to memorize alkanes, is CnH2n plus 2, okay? Where N is the number of carbons within the hydrocarbon. So if I have two carbons that are singly bonded together, it would be C2, and then I plug the 2 in over here, and I have 2 times 2, which is 4, plus 2, which is 6. So C2H6 would be that, okay? So, for example, this one has 1, 2, 3, 4, 5, 6 carbons, okay? So I'd plug 6 in over here. Now, since they're all singly bonded together, we can assume we can use the alkane formula. So it'd be C6, and I plug 6 in over here, so it's 6 times 2, which is 12, plus 2, which is 14. So if I count these up, it should be 14. So 3, 5, 7, 9, 11, 14 hydrogens. Okay? So it's C6H14. Cycloalkanes, they are alkanes that form a ring-like structure with their carbon atoms. So it's where the carbons are singly bonded together, but the carbons form a carbon ring. They also can become saturated because they're so easily bonded together, so that means they can be compressed together in higher concentrations. Their generic formula is CnH2n, so it's 2 less than the regular alkane formula. So if I count up the number of carbons, 1, 2, 3, 4, 5, 6, okay, that's going to be C6, which turns us into H12. So I can add those up, 2, 4, 6, 8, 10, 12. So I have C6H12. The reason why it's 2 less is because carbon wants to form 4 bonds. And so in this, each carbon is connected to, except for these 2 right here, okay, they're connected to 2 other things. But to form a ring, this carbon has to bond with this carbon over here. So they have to let go of one of their hydrogens to just form 4 bonds. Okay, so alkenes and alkynes. Alkenes are carbon compounds where at least one pair of carbon atoms is double bonded together. They can only be unsaturated. Due to their bonding, they do not want to be saturated in the way alkanes do. The generic formula for this is CnH2n. Now, if you notice, this formula is the exact same formula for cycloalkanes. So the formulas work for the exact same thing, but it depends on their structural formula. It depends on if you're talking about a cycloalkane or an alkene itself. Okay, so this would be an example of an alkene, so we'll just demonstrate it. So I have 1, 2, 3, 4 carbons. Okay, there's at least one double bond, so I know it's an alkene. So I plug in and have 4 carbons for N, which means I should have 8 hydrogens. So 3, 4, 5 plus 3 is 8. So it's C4H8. Alkynes are carbon compounds that have at least 2 carbons that are triply bonded together, so triple bonds. They can also only be unsaturated, which means due to their bonds, they're unstable and they don't want to stick together more than they have to. Their generic formula is CnH2n minus 2. So it's kind of, if you memorize the alkane formula, instead of the plus 2, you put minus 2, you can remember it that way. So if I look at an alkyne, I have 1, 2, 3, 4 carbons. So that 4 goes here. So I have 4 times 2, which is 8, minus 2 is 6, and I only have 3 and 6 hydrogens. And again, carbon only wants to form 4 bonds. So since each of these carbons are bonded triply together, they can only form one more bond that connects the other carbons, so they have no hydrogens attached to them. So that forms C4H6 for formula. So naming hydrocarbons. To start, if you're given a structural formula, you must identify the largest continuous carbon chain. After you identify the largest continuous carbon chain within the formula itself, based on the number of carbons that are in that chain, you use a designated prefix in front of it to indicate the number of carbons in that longest chain. Then the name ends with A and E to represent alkane, because alkane ends with A and E, so therefore an alkane that we're talking about ends with A and E. E and E for an alkene, Y and E for alkyne. So there are prefixes you're going to have to memorize. Nice thing is they're very, very similar to the covalent compound prefixes that we learned before, except for a couple of other ones. So meth, not the drug, meth represents 1 carbon within a chain. Eth represents 2. Prop, which propane, which you've already heard is an alkane that's consisted of a long 3 carbon chain, that represents 3. Butane, which you have in lighters, is a 4 carbon chain fluid, a hydrocarbon that you can burn. So that represents 4. And then the other ones are ones that you're really familiar with. So we have pent, hex, hept, oct, non, and dec. As you notice that these ones don't have A's in them. okay, because it's just the regular root word. But really, if you have already memorized the 5 through 10 for the covalent compounds, then you really only have to memorize 4 more. Okay, so just think about that when you're starting to learn these things. So let's do a couple examples. So I have a carbon chain right here. First thing I need to do is identify the longest carbon chain, which is C1, 2, and 3. So it's a 3-carbon chain. And they're all singly bonded together, which means it is an alkane. Longest carbon chain is 3. Okay, so which means it's going to be propane, because 3-carbon chain is the prop prefix, and then since it's an alkane, it's A-N-E, so it's propane. And that is C3H8 because it's CN 2N plus 2. Okay, so 3, and then you have 2 times 3, which is 6, plus 2, which is 8, and you can count them up. So 3, 5, 8. This one is singly bonded, so we know that's an alkane. Then I count up the longest carbon chain, which is 1, 2, 3, 4. So that has 4 carbons, which means that its prefix is going to be bute. So it's going to be called butane. Okay, so a 4-chained alkane. And again, alkanes is CnH2n plus 2. So I have 4, so it's going to be C4 plus 2 times 4, which is 8, plus 2 is 10. I count them up: 3, 6, 8, 10. So you get C4H10. Now this one is a weird one. So if I count up the longest carbon chain, 1, 2, 3, okay, that's prop. But if we recognize how many carbons and hydrogens that there are, they're equivalent to exactly this same formula. Okay, so this is an alkane. The longest carbon chain is 3, however, it has the same formula as butane. So since it has the same chemical formula as butane, we know it's an isomer of butane. So which means it's just going to be called isobutane. Okay, so again, it's 4 carbons, 10 hydrogens. So be careful when you're looking at this, when you're counting up the carbon chain, because if it has a similar formula to an alkane that's already been identified, then it's the isomer of that. All right, so we have carbons that are in a cycle. So they're all singly bonded together, so we know it's an alkane. And since it's in a cycle, we just count them up: 1, 2, 3, 4. Okay, so we have a longest chain of 4 carbons continuously, and it's in cyclic form or in a ring. So we know we're going to put cyclo in front of it, okay, because it's a cycloalkane. But then we need to identify its 4. So 4 is the prefix for bute, so it's going to be cyclobutane, okay. And again, that's C4H8 because that follows CnH2n. So 4 carbons, 2 times 4 is 8. Okay, now this one has a double bond, so now we know it's going to be an alkene. Okay, now since it has a double bond, still the longest chain is going to be 1, 2, 3, 4, 5. Okay, so the longest chain is still 5, so it's going to be pent, so it's going to be pentene. Now, alkenes follow the exact same formula as cycloalkanes. So that's going to be CnH2n. So instead of 5 carbons, it's going to be C5H10. And then lastly, we have an alkyne because it's triply bonded between 2 carbon atoms. Okay, and then the longest chain is 2. So we're going to use the prefix of eth. So it's going to be ethyne. And that is C2H2. So remember, it's CnH2n minus 2. Okay, so the 2 carbons turns to 2 times 2, which is 4, minus 2 is 2. And that's where you get the 2 H's from. All right, so again, a lot of information. If you have any trouble with the structural formulas, what isomers are, naming, everything like that, organic compounds are not as prominent in this course, but as you go further into other chemistry courses, it will. So this is kind of a brief overview of what organic chemistry is, but it's very important to know what type of gases we'll be working with in class and what they're actually made of, because as we go on to further units where we do what's called combustion reactions, you can produce organic compounds, and they utilize organic compounds to actually make fire and stuff like that. So that's where we have to go a little bit deeper into organic compounds and where they actually relate to. So again, if you have any questions, please come talk to me, email me, do whatever you need to do. Otherwise, thanks for watching this video, and hope to see you in the next one and in class. Bye.